All right, so now we know a little bit about rate laws. We're going to try to do a problem where we will try to figure out what the rate law is based on a set of data about what happens as we change concentration in that reaction. So this is basically maybe about half of this particular chapter. We'll be evaluating this type of experiment or set of experimental data. We're given a set of experiments. We want to determine what the rate law of the reaction is. We've got the reaction given. So what we should be able to do right off the bat is kind of fill in just the pieces of the rate law. We've got rate on one side is equal to the rate constant K, right? And then there's going to be a term for each of the reactants. So hydrogen peroxide, iodide, and H plus here. And there'll be an exponent here, and these exponents relate to the mechanism of the reaction. We need to figure out what the value of those exponents is. So I just called them x, y, and z. So we have hydrogen peroxide to the xth power, excuse me, iodide to the yth power, and our H plus or protons here are to the zth power. What we need to do is look at the set of experimental data given here and use it to evaluate what those exponents are. So I'm going to show you pretty explicitly here for the first one, and then we kind of have to do that sort of analysis for all the rest of the comparisons. So the first thing we're going to do here is look for a situation where one of the components changes concentration between two experiments, but the other two components of the reaction, in this case, stay the same. So if I compare experiment 2 and experiment 1, going from 1 to 2, the concentration of hydrogen peroxide here is doubling, concentration of iodide is staying the same, and the concentration of H plus is staying the same. Right? And the last column over here is the rate. Now usually this is called initial rate because rate's faster early in a reaction. You try to measure the rate as quickly as possible because you get better data that way. So what I want to do here is compare the second experiment in this table to the first. And I'm going to do that by ratioing the rate laws here. So I'm going to take the rate of experiment 2. I'm going to divide that by the rate of experiment 1. Now I'm putting 2 on top because it's the larger value. So that means the ratio I'll get here is 2. You can do it the other way, but then you get 1/2. Most people are a little more comfortable, right, raising 2 to exponents than raising 1/2 to exponents, even though essentially it's the same thing. Okay, ratio of rates on one side. Now if rate is equal to this, that will also be present on kind of the right side of the equation. So I'll have the rate constant times the concentration of hydrogen peroxide to the xth power, iodide to the yth power, H plus to the zth power. Right? And all of those are for experiment 2. So let me put in some subscript 2's there for my concentrations. For experiment number 1 in my table, the rate of 1 is going to be equal to the rate constant times concentration of hydrogen peroxide to the xth power. Now that's got a 1 there because that's from the first experiment. Iodide from the first experiment, protons from the first experiment. Now, there's a lot that's going to go into designing this experiment because what we need to do here is cancel out most of this information. The rate constant is for the reaction, so it's the same between experiment 1 and experiment 2. Right? And the way the experiment was designed, the concentration of iodide and the concentration of H plus did not change between experiment 1 and experiment 2. So those are the same on the top and the bottom of the fraction. So those completely cancel out. So with all that canceled out, we're left with the ratio of rates on one side of the equation. So rate of 2 divided by rate of 1. And then on the right side of the equation, it's the ratio of the concentrations of hydrogen peroxide. And those have this exponent x in there. Okay, now looking back at the data in the problem, the rate of 2 was 2.3 times 10 to the minus 6th. The rate of 1 was 1.15 times 10 to the minus 6th. So that's 2.3 times 10 to the minus 6th over 1.15 times 10 to the minus 6th. And you could probably see that's equal to 2. Now, the other side of this equation is the concentration, the ratio of the concentrations of hydrogen peroxide. 0.02 over 0.010, that's the ratio of my rates. Now, these are both to the x to power, so mathematically I could write it like that as well. Since that ratio is also 2, but it's raised to the x power, I end up with 2 is equal to 2 to the x to power. Well, that means x is equal to 1. So the exponent that describes hydrogen peroxide in this reaction is 1 in my rate law. Okay, so I've got one of those exponents now. I need to do the same thing for the other two components. So let's try to do this in a little quicker fashion, right? Without having to write out all the things that cancel out. Let me just try to evaluate what's happening in the problem. So if I look at experiment 1 and experiment 3, hydrogen peroxide stays the same between those two experiments, right? That's good. That's what I'm looking for. I already know what happens relative to hydrogen peroxide in my rate law. Iodide goes from 0.01 to 0.02, so it doubles. And H plus from 1 to 3 is also the same, right? So just like we did up here, we can cancel out everything except the contribution of the concentrations of iodide. Now, the rate between 1 and 3 also increases by a factor of 2. Okay, so this first whole set, this was trying to figure out the dependence of hydrogen peroxide in my rate law. Comparing experiment 3 to 1, we'll be evaluating how iodide is described in the rate law. So if I take the rate of 3 divided by the rate of experiment 1, we said that's 2. That's going to be equal to, again, rate constant is going to cancel out, peroxide and H plus are going to cancel out, so that'll just be the rate of iodide in experiment 3, rate, concentration of iodide in 3 divided by concentration of iodide in experiment 1, and that whole thing will be raised to the yth power. That concentration is also a factor of 2, or ratio of 2, and that's raised to the y power. So y here will also be equal to 1, right? And remember what I said before about stoichiometry? It's 1 for hydrogen peroxide, so that's accidental that this turned out to be 1. It's 3 for iodide up here, but in the rate law it's only 1, right? And we'll see a little bit later what that tells us about how the reaction is happening. Okay, but one more that we need to do, and that is H plus. Now for H plus, I'm going to look at experiment 1 and experiment 4. So from experiment 1 to experiment 4, hydrogen peroxide is the same, right? And iodide, they're both 0.01. Iodide is the same, but H plus goes from 0.005 to 0.01, so that changes by a factor of 2, twice as much in experiment 4. And when I look at the rate though, the rate for experiment 1 and the rate for experiment 4 is the same. So comparing 4 to 1, that's how I'm going to get a handle on H plus and how H plus is relating to this rate law. The ratio of my rates, rate of 4 to rate of 1, is 1. They stayed the same. That's going to relate to the concentration of H plus in 4 relative to 1, and that, I said, was raised to the zth power. Well, the concentration did double in 4, so that's 2 raised to the z. Now, you raise anything to the 0th power and it's equal to 1. So in this case, that tells us z is equal to 0. So we determined, go back to my original color, for H2O2, we got x equals 1. Another way to describe that is first order. The reaction is first order in hydrogen peroxide because the exponent is equal to 1. The reaction would be first order in iodide, I minus, because that exponent is equal to 1. And since we got 0 here, we would say the reaction is 0th order in the concentration of H plus. Now that's got consequences for mechanism, which we'll talk about eventually, a couple pages away. But this allows us to finish our rate law. The rate is equal to the rate constant concentration of hydrogen peroxide would be raised to the first power. Now, raising something to the first power doesn't really do anything, so we don't usually write those ones in there when you're just looking at a rate law. Iodide is also to the first power, but H plus would be to the 0th power. Now, you raise it to the 0th power, that's always equal to 1. So we could really simplify this rate law. It's only dependent on the concentration of peroxide and the concentration of, that was a bad I, of iodide. We could leave H plus completely out, since no matter what the concentration is, it won't change the value we would calculate over here for rate. Okay, we've got one more example of this coming up.